So now moving to design F, which says that fan in result, move inputs and wait stays. So this will be evident after we derive the result. Okay, so now the first step is to choose the projection vector. So projection vector D is 1 and 0. Okay, and then you have to choose processor space vector. PT. So the processor space vector and projection vector should be orthogonal. Okay, so one of the choice can be 0 and 1. So you can verify that pt dot d, that is 0 1 multiplied by 1 0. This is 0 into 1 is 0, 0 into 0 is 0. So you can verify that pt dot d, that is 0 into 1 into 0 1, that is a row matrix, and the projection vector is 1 0, a column matrix. 0 into 1 is 0, 1 into 0 is 0, so 0 plus 0 is 0. Then the scheduling vector is chosen as 1 and 1, and the product of scheduling vector and the projection vector should not be equal to 0. So again you can verify std should not be equal to 0. So 1 into 1, so scheduling vector multiplied by projection vector gives you 1. So now you have to map the three edges present in dependence graph. This is weight, this is input, and this is output. So 1 minus 1, weight is given by 1 and 0, and input is denoted by 0 and 1. So you have to map these three edges present in the dependence graph by using formula PTE, so and STE, where P transpose E, E corresponds to these edges, so P transpose multiplied by E, that is the edge in the corresponding systolic array, and the product of S transpose and E is the delay of that particular edge. So now for this we will prepare a edge mapping table for design F. So we have edge weight given by 1 and 0, input given by 0 and 1, and result, or you can say output, given by 1 and minus 1. So P transpose into E for weight, that gives 0, and S transpose into weight gives 1, simple matrix multiplication. P transpose into input will give you 1, and S transpose into this edge will also give you 1. Result into P transpose will give you minus 1, and scheduling vector and result product of this two will give you 0. So now to derive the systolic array from this, I have to calculate two more factors. First is the product of pt into I. So let I is I comma j. Okay, and in the matrix form I can represent I transpose I and j, a column matrix. So I and j are index present in dependence graph, and the product of p transpose into I will give that the node or processor that will execute I. Okay, so 0 1 multiplied by I. So this is I transpose I is I and j. So the value is j itself. Okay, again it is j, and the value of j is 3, because in our FIR filter y is equal to w0 xn plus w1 xn minus 1 plus w2 xn minus 2. J corresponds to this weight. In dependence graph, weight were represented by the horizontal axis. Okay, so w0, w1, w2. So j is 3. So we have to use 3 processors. And to calculate the execution time of I, we have to find the product of S transpose I. So this is 1 into I and J. So this gives I plus G. So now I can derive the corresponding block diagram and space-time representation. So J is 3 means I have to use 3 processors. Processor 1, processor 2 and processor 3. So J is 3, that corresponds to 3 number of processors. Starting with the weight, this coefficient, the value of PTE is 0, so it corresponds to H, this corresponds to delay. Okay, in systolic array. So H is 0, so I can represent 0H by like this, and the weight is 1, so 1 delay is associated with it. Okay, so for all processor I have to assign a weight because the structure is similar. Input H is plus 1 means moving in right direction. Okay, so this is plus 1, this is minus 1. So input is plus 1 means moving in right direction with delay 1. So, so this is input, and between these two processors the edge will have 1 delay. And output is minus 1 means in this direction, right to left, with 0 delays. like this. So this is block diagram of the F design, and I can derive a low level implementation from this. So input xn with the 1 delay, and this is going to a multiplier and adder. This will also go to a multiplier and adder, and one more delay. This will again go to a multiplier and adder. So this, the combination of a multiplier and adder, represents this processor. So this result output should be transferred to the adjacent processor with 0 delays. And weight will be given to the multiplier. So this is the way we draw weight with 0 delay. This is the way we draw weight. This corresponds to W0, this corresponds to W1, and this corresponds to W2. This is a low level implementation. Somewhat close to hardware. So this is again a known structure, and this is direct form 1 of the 3-tap FIR filter. So in this architecture you can see that input is moving from left to right with one delay element. The output moves from right to left with no delay element, and weights are fixed. Okay, so that's why we say that output is fanned in, and that's why this design is known as fan in result. Move inputs and weight stays. This can also be verified by space-time representation of the F design. Okay, so for this dependence graph you have to map this into space-time representation, and it has two axes, T prime and J prime. So J prime is, we have already calculated, it is product of P transpose into capital I, where capital I was I and J, any index in the dependence graph. So J prime is equal to J. Okay, so the J axis in both the graph are similar. So in this J axis, for any particular value of J, it corresponds to the weight. Okay, so the space-time graph, the case will be the same. So this corresponds to W0, W1, W2. T prime is given by S transpose I and J. This is I plus J. So the time axis is given by I plus J. So in this graph, I plus J corresponds to this value, output value, Y0, Y1, Y2. The equation for this Y0, Y1, Y2 and any output is kind of I plus J. Okay, so in this graph, in a space-time graph, this T prime corresponds to I plus J. Means if I draw a vertical axis, that will correspond to this output Y0, Y1, Y2. Okay, and then input is moving from left to right with one delay. So at this point the product of W0 and x0 will be at 0 point, x0 will be at this point. The product of W0 x0 will give y0 at this point. Now in the next cycle x0 is moving, so x0 will move to this point. So the product of w1 x0 plus w0 x1, so x1 will be introduced at this points. Okay, will give you y1. Also the projection vector is 0 and 1. This corresponds to upward direction. Okay, so at this point x1 will introduced and x1 into w0, the result will be projected in upward direction, that will be added to x0 w1, so that corresponds to output y1, that is x0 w1 plus x1 w0. Similarly at this point x3 will introduced, and by this time x1 will move to this point and x0 will move to this point. x2 w0 will be projected in upward direction, x1 w1 will be projected in upward direction, and finally added to x0 w0, that will give result y2. Okay, so weight stays, weight is not moving. Okay, this all this horizontal line will be mapped to the same processor because we have chosen our value of d as 1 and 0. This corresponds to this direction, so all this will be mapped to the same processor. So weight stays. Okay, weight is applied to the same processor. Input is fanned in. This intersection corresponds to different processors. Okay, so input is fanned in, y0 is fanned into all this processor, y1 is fanned into all this, y2 and so on, and x0 is moving because initially x0 will be at this point, then it will move to the next processor, then next, then same y x1 will start from this point, then it will move to this point, then this processor. So this processors correspond to similar computational element.